This conference will now be recorded.
So very good evening, students. Today we'll be discussing few more problems on magnetism chapter. So these are all from JEE Mains paper, previous year's paper. Okay, let us start our discussions. The first question says that the dipole moment of a circular loop carrying current I is M, and the magnetic field at the center of the loop is B1. When the dipole moment is double, by keeping the current constant, the magnetic field at the center of the loop is B2. You have to find out what is the ratio of B1 and B2. I'll make you clear the question, what it says. The question says that suppose there was a circular loop like this. So magnetic moment due to this, suppose the current is flowing in the clockwise direction like this. So when a current flows through this, it will be associated with a magnetic moment, you know that, and that is written as M. Suppose this is loop 1. Loop 1, let us say L1. So the circular loop will produce a magnetic field along the axis, right? We have already learned from Biot-Savart's application of Biot-Savart's law. It will produce a magnetic field along the axis, and at the center the magnetic field of this loop is given as B1. Now we have taken another loop which actually carries the same current, okay, carries the same current in the same direction I. This is loop 2. In this case, the magnetic moment M2, suppose this is M1 and this is M2, this is seen to be twice M, okay, by keeping the I constant. So what will be B2? That is the question. Suppose the magnetic field at that center of that loop is B2, then you have to find out what is B1 over B2. So the ratio of B1 to B2 you have to find out. This is the question. So in this case, if you want to solve this problem, first of all we need to know the definition of magnetic moment. So what is the definition of magnetic moment? The definition of magnetic moment is M is equal to I, that is the current flowing through the loop, and the area of the loop. So this is actually the formula for the magnetic moment associated with any type of loop, okay, whether it is square loop or circular loop or rectangular loop, whatever it is. This is the formula for magnetic moment associated with that loop. Now I have circular loop. Life is so simple. So here what I'll do, first of all, see this B at the center of circular loop. B at the center of circular loop. We have already learned. What is that? Better to remember the formula. 2r. So mu0 I by 2r. 2r is the radius. Okay. If this is r1, let us say this is r2. Okay. So this is the master formula which you should remember, mu0 I by 2r. So this is the magnetic field at the center produced by a coil when I current is flowing through it. We are just taking the magnitude because there is no other things important here. Anyway, so look this formula. If I write M1, then I will write I into A1, and M2 I'll write I current was kept constant, so I into A2. A2 is the area, so area has to be different. Okay, to get the same magnetic moment with the same current. Sorry, not same, double magnetic moment. At least area has to be increased or decreased. Let us say it has to be decreased because m2 is equal to 2m1. Okay, so now we'll just apply this condition is given. So m2 is equal to 2m1, which is saying that a2 is equal to 2a1. This implies if I just write m2 is equal to I a2, let me write that, and this 2 into m1 is I a1, so I goes off from both sides, so that's why I have written a2 is equal to 2a1. Okay, with this, look, I'll just erase this part. Okay, so with this what we'll get, see, we'll get the relation between the radius, because for a circular loop area is pi r2 square, this is pi r1 square. Okay, along with 2 multiplied here, this goes off, sorry, pi will be going off from both sides. Now we have got a relationship between, so here b1 by b2, so let us write r1 by r2. So r1 by r2 will be r1 by r2 will be 1 by root over 2. R1 by R2 will be 1 over root over 2, because see, this R1 square by R2 square is equal to 1 by 2. Okay, so from there, so what we have got a relationship. I'll write over here R1 by R2, that is this. Okay, all right, after getting this, what we can do, we can just put this radius. See, we'll write the magnetic field at the center for both. B1 is then mu0 I, this I is constant for the loop 2 also, and this is 2r1. Okay, here B2 I will be writing mu0 I, these are the same factors, only thing will be this r2 is different. Okay, now let us take the ratio b1 by b2. If we write b1 by b2, or okay, so b1, we have to find out b1 by b2 ratio, right? So let us write this b1 by b2 is equal to, see, b1, so this will be in the denominator and r2 will be in the numerator. Okay, rest of the things will go off because all are constant, mu0 I constant, 2 is constant, here 2 is constant anyway. So if I take the ratio, I'll get r2 by r1. So here we have got ratio r2 by r1 to be what? Root over 2. So this is actually the answer. So look, the fundamental point is that you have to remember what is the definition of magnetic moment, that is I into A, and you have to guess that here, since the current is kept constant, then the radius has to be increased, or there should be a relationship between the radii of these two loops, and from getting that relationship, we'll put the r1 and r2 after taking ratio of magnetic field at the center for both the loops. And this is also important to remember, or at least you should be able to write the formula for the magnetic field at the center of the circular loop. Otherwise it will be difficult to derive and solve it. It will take little more time. So better to keep this in mind and this definition of the magnetic moment in mind. That will help you to solve it in very short time. Okay, we'll go to the next problem. So this problem is again an interesting problem, and this is also from JEE Mains paper 2017. See, a magnetic needle, we know if a magnetic needle is kept in a uniform magnetic field, if you remember, if you keep a magnetic needle okay, keep in a uniform magnetic field and just give a little bit angular displacement. So it will, what it will do, you have N and S. So this is the direction of magnetic field. So what it will do, actually it will experience a torque similar to that of our electric torque. So here also there will be a torque acting on that. Okay, so from that it will actually try to oscillate. So torque will be actually given by I into A into, so this is mb cross B. So mb sine theta is mb sine theta. Okay, this is the torque. This torque will be equal to uh, mb sine theta. So torque, this is the torque. This will be balanced by what? This will be imb. Okay, imb. Anyway, so there will be a relationship. You will be, actually this is the force and this is directly uh, this is the torque. So torque will be directly proportional to theta. So yeah, so this is how you have to actually uh, arrive to the oscillation, time period of oscillation. So time period of oscillation will be written as 2 pi. Obviously there will be, okay, there will be moment of inertia. So that moment of inertia will actually I omega. So this will be equal to the mb sine theta into I. So I into a magnetic moment, torque will be given by I omega. So these two will be equal. Okay, from there you'll be able to find out the formula. Okay, so all right, so torque for the material of this is, if the I is the moment of inertia, okay, I is not the current over here, and see the torque is mb sine theta. Okay, magnetic moment mb sine theta, theta is small angle. Okay, so mb theta. So m into v theta, b is the magnetic field, m is the magnetic moment, and this is theta. So from here actually you'll get omega will be mb theta. The omega is actually the angular frequency. So mb theta by I is this. So from here actually we know t is equal to 2 pi by omega. So omega, so it will be actually 2 pi square root of I by mb. Okay, so okay, so from here we have to find out. Okay, all right, so this is the formula. So 2 pi into root over I by mb, square root of I by mb. So this is the formula for time period of oscillations for that needle, compass needle or magnetic needle, whatever you say. Okay, so we'll now check this problem. A magnetic needle of magnetic moment. So magnetic moment m is given. This is magnetic moment, and moment of inertia I is given. So this is my moment of inertia we got, is performing a simple harmonic oscillation in a magnetic field. Magnetic field is also given. See, I have all the parameters m, I, b. All the parameters I have. If we put here, so main point is that you have to remember this formula. Okay, better to remember this, otherwise wasting time in like deriving that. So I is given as 7.5 into 10 to the power minus 6 kg meter square. Okay, then M into B. M is given as so this is given as M is given as 6.7 into 10 to the power minus 2 ampere meter square, and the magnetic field B is given at 0.01 Tesla. Okay, all are in SI unit, so no need to bother. You just make the you just do the calculation. After doing calculation, what you will get actually, you will get 0.66. Okay, 0.6 is this. So this is actually the time. This is second. So this is time period, means for one complete oscillation. Time period means for one complete oscillation you will get this much time. It will take this much time. For 10 complete oscillations, that means 10 into t. So 10 into t will be 6.65 second. So this is the answer. Okay. So for 10 oscillations, you need 10 into time period, and this is actually the time period. So you have to just use this formula. So I is here actually moment of inertia, and M is magnetic moment, and B is the magnetic field induction or magnetic flux density. Okay, so this is the answer. All right, we'll go to the next problem. This is a very simple problem. You should actually remember few points over here. Let us first read the question. Hysteresis loop for two magnetic materials A and B are given over here. Okay, these materials are used to make magnet for electromagnetic generators, transformer core, and electromagnetic core. So then these two materials, out of these two, which one is suitable for using them, like which one of this is suitable for the use of the following way? What are the way? Suppose A can be, the option is saying A can be used for electric generator and transformer. A is this. Okay, then A can be used as for electromagnet, and this B can be used as generator. Okay, generator. A transformer A can be used as transformer, and B can be used as electric generator, and B for electromagnet and transformer. Okay, let me just tell you few points about this curves. So material, so there are two different materials. Actually question is that there are two different magnetic materials, which one can be used for making electromagnet or transformer core or generator, etc. So that you have to find out. See, the material A, it is actually called hard magnetic material. Hard magnetic materials. Magnetic material. So why hard magnetic materials? Because it has greater coercivity. So if we want to demagnetize it, we need greater field in the reverse direction to make the magnetization zero. That means when this is 1.1. Second point is, if this kind of materials are becoming magnet, then actually to demagnetize you need to provide very large field. So it can become uh, it can be used as permanent magnet. Permanent magnet. So these materials are called hard materials, which have greater hysteresis and more coercivity. It will be very difficult to make the magnetization zero once it is magnetized. So it is the some like material which can be used for permanent magnet. Okay, permanent magnet. So the see electric generator, transformer, electromagnet, wherever there is a hard material or permanent magnet is needed, so there we can use this material A. So the option A, electric generator, that is fine. But for transformer you need soft magnetic material. So this is called hard magnetic material because coercivity is more. And this is a very gentle loop. You can see that the area under the loop is not very large, and also uh, uh, we can see the coercivity is very low. Coercivity is very low. That means this material can be easily magnetized and demagnetized. That's why it is actually called soft magnetic material. So to make electromagnet, you need soft magnetic material. So this B can be used as electromagnet, and also for the transformer you need not have large hysteresis area, because if you have very large hysteresis area, then more loss. In this case, more heat loss or more energy loss. More energy loss as heat. More energy loss will be there in case of material A, because it is hard material first of all, and also it has greater area. That means it actually will make you lose greater energy as heat energy. Okay, heat energy. That's why if you use this kind of material, so that your device after running for some continuous running for some time, some long time, at least 3-4 hours, then also the device will be actually heated up due to this hysteresis. Okay, so look here, electric generator cannot use this A because it is a very soft material, and transformer can use, or transformer has to use soft magnetic material. But here, since this option is wrong, A cannot be used. Okay, so A cannot be used for transformer. A can be used for generator. That is fine. So that's why this option is not correct. A can be used for electromagnet. That is also very wrong, because it has greater hysteresis loop. So if we use this, and also this is hard material, so if we make use of this material to prepare electromagnet, then it will be difficult for us to actually serve the purpose of an electromagnet with this, because electromagnet actually the magnet which loses its magnetization after switching off the fields or the current through them. Okay, so B can be used as a generator. That is wrong. This is also wrong. Sorry, this is correct. A can be, no, this is also not correct. A transformer and B electric generator. A transformer, it cannot be used as transformer because hysteresis loss is more. And B is electric generator. Electric generator, it may be used, but since this portion is wrong, this whole sentence is wrong. Okay, now B for electromagnet and transformer. See, B is the actually soft material. It can be suitably used for electromagnet and transformer. Okay, so this is actually uh, this is with this. So okay, so this is with the magnetic materials we have seen. Okay, now we'll solve a very good problem. This is a very interesting problem, and you will be actually thrilled to solve this problem. Here the problem states that a current loop having two circular arc, it is like this, one arc and another arc like this. Okay, so there are two circular arc. They said there are two circular arc. as you see from here. Circular arcs, it is actually carrying a current I is equal to 10 ampere. As you see in the figure, the angle which subtend by the ends of these two arc is 45 degree. That is very clear from the figure. And you know the radius of this particular arc is 3 centimeter, and radius of this this particular arc may be 2 centimeter. Okay, sorry, 2 plus 3, 5 centimeter. Now we will be actually using Biot-Savart's law. See, magnetic field for any current element can be obtained as B is equal to mu0 by 4 pi into I dl sine theta. I'll just go with magnitude, dl sine theta by r square. If you write in terms of magnitude, so this is proportional to dl cross r. Okay, so B is proportional to dl cross r. So look here, among this, all the sides, so this is the side RS, this particular side. Magnetic field due to RS and magnetic field due to PQ will be obviously 0. Okay, because see the sine theta is 0 because dl, okay, dl cross r, dl is this one and r is this. So dl cross r, due to these two, the contribution will be actually 0. Contribution for this straight portions will be 0 because the angle between them will be actually, so this angle is anyway 45 degree, but this angle, so these are straight portions, they will be making angle 0 with this O point. Okay, so that's why the magnetic field due to this straight portions are 0. Okay, so now we have got these two arc, these two arcs. So to calculate the magnetic field due to these two arcs, see what we can do. And first of all, you can see that this is actually carrying current in the clockwise direction, this is carrying current anti-clockwise direction. So magnetic field obviously will be subtract, like you have to first of all find out magnetic field due to this one. Let us say magnetic field due to this one is B1 and this due to this is B2. So B1, actually B1 and B2 can be written in the same formula. See, the formula for this calculation of this is mu0 I theta divided by 4 pi r. So B1 is equal to, B1 means magnetic field due to this particular arc at the center. So this is mu0 I theta by 4 pi r1. Okay, if this radius is taken to be 1. Okay, this much is r1. Okay, now this much, the whole radius is r2 taken, and since I'm taking this as positive, so this b I'll be taking as negative. So mu0 I, similar formula, just the r will be different. Okay, so this, now this will be actually opposite to the magnetic field of this, so that's why net magnetic field will be at the B, net magnetic field will be mu0 I theta by 4 pi whole into 1 over r1 minus 1 over r2. So this is the formula, mu0 I theta divided by 4 pi whole into 1 over r1 minus 1 over r2. So in this case you have to now use the value of theta wisely. So this theta you have to actually convert into radian, and then you have to write it. Okay, so 45 degree, so theta is actually 45 degree, so 45 degree is nothing but pi by 4 radian. So this is what you have to use for both of them. And see, if you put this mu by 4 pi is actually 10 to the power minus 7. This I is actually 10 ampere. Okay, 10 ampere, 10 ampere. IV, sorry, this is theta. Theta is actually pi by 4 radian, and this will be 4 pi, and whole into 1 by 3 10 to the minus 2, so 100 by 3 minus 100 by 5. Okay, so this is what, if you write and solve it, so I have told you the formula. You just put this theta will be actually pi by 4. Okay, so now if you put the values, you will be actually able to get, in fact calculation will be showing you that this is 10 to the power minus 5 Tesla. Okay, so this will be the answer, 1.0 into 10 to the power minus 5 Tesla. This is the answer for this question. So I'll just summarize what I have done. See, I have 4 portions, this straight portions will have 0 angle with the radius. So that's why when I will be doing dl cross r, that dl cross r, that means dl sine 0 degree, so that would make it 0. Now you have to calculate magnetic field for both the arcs, and since the magnetic field is in the opposite direction for both the arcs, that's why there will be a net magnetic field at this particular center. Okay, and that answer will be this one. Now we'll take up few more problems. So I'll just write down. Okay, let me take this problem. In an experiment, in an experiment electrons are, I'm writing electrons like this, electrons are accelerated from rest, accelerated from rest by applying a voltage of 500 volt. Calculate the radius, calculate the radius of the path radius of the path if a magnetic field, 100 Tesla, sorry, millitesla is 100 millitesla is applied. Okay, so this is the question. So there are few options. I'll just give you the options also here. Options are 7.5, okay, then B 7.5 into 10 to the minus 4 meter. These are all meter. And option C is saying this would be 1.5 into 10 to the power minus 7. Calculate the radius of the path. I'm sorry, this is this is 7.5 into 10 to the power minus 3. It says 3 meter. D is given as just 7.5 meter. You have to actually solve this problem. So what is the problem? Like electrons are accelerated by applying a voltage. Okay, so that is what is given. Now you have to calculate the radius of the path. Okay, if the magnetic field 100 millitesla is applied, it is actually the question from JEE Mains 2019. Okay, we have got the question. We'll just try to solve it. So look, actually what we know for a circular path, so the magnetic force on any charged particle will be equal mv square by r. This will give you the centripetal force. So bqv. bqv. All right, bqv. Now look what I'll do. I'll just keep this part alone here. bqv. Okay, so v will be going up from here. So b is okay, bqr. Okay, bqr, and r can be written as m by bq into v. V is the velocity. See, when an electron is given, like electrons are accelerated by 500 volt, then it will have kinetic energy half mv square is equal to E into the applied voltage V. So that is 500 EV. Okay. So this is the thing given. The kinetic energy is given as 500 electron volt. So from here, actually we can make use of the velocity. See, we will write 2m. Let me just not write this one first. Let me be with the formula itself. So 2ev by m and square root of this. Okay, 2ev by m. Now look, if you just put it here, so m by bq is fine. Now you have to put v. V is equal to, this is actually electron volt. E and V inside. So 2 EV divided by M. That means, the formula is becoming square root of so square root of 2 M EV divided by, if I just keep this uh, in the denominator outside the square root, then it is fine. 2MEV by BQ. What is this M? M is actually the velocity of. So look what we have got. We have got the formula for radius is equal to 2MEV divided by BQ. Okay, this is the formula for getting the radius. Okay, BQV all right. So from here we have to find out. Look, then R is directly proportional to, the question was actually to find out the radius of the path. Radius of the path. So we have to directly find out what is the radius of the path. Okay. So look here, we'll just write the values given. Okay, write the values given. See, this is 2 is factor, M is 9.1 into 10 to the power minus 31 kg. Okay, so electron volt I have to make it joule. So 500 into 1.6 into 10 to the power minus 19 and divided by B was given as 0.01 Tesla, I guess. Oh, 100 millitesla, yes. So 0.1 Tesla. Next. So B and Q. B is actually, B is given as 100 millitesla 10 to the power minus 3, so it will be 0.1 Tesla, and Q is again having charge, electronic charge, positive charge I am taking. Okay, so this is 1 Tesla. These are with suitable unit. Now if you solve this problem, this calculation, if you solve it, then what is the answer you should get? Actually you should get this R is equal to 7.5 into 10 to the power into 10 to the power minus 4 meter. Okay, minus 4 meter. I'm not doing this calculation rigorously. I'm just leaving for you. Just do it and see. It should come as this. Okay. So this is actually fundamental thing you should remember, or you should be able to derive. That's all. Okay. So now we'll go for another problem and then we'll stop. So let me erase this. So this problem is very, very interesting. You can see this is problem number 6 then. A particle of mass m, a particle of mass m and charge q and charge Q is in electric and is in an electric and magnetic field. Electric and magnetic field given by magnetic fields given by E is equal to 2I plus 3J. Okay, that means if you just draw X, Y, Z somewhat, so this is suppose Z, this is Y, and this is X direction in the Cartesian coordinate system, then the electric field is in this plane. Okay, in this plane 2J, and the direction can be obtained from here itself. So tan theta will be, sorry, theta will be tan inverse 3/2. So this angle, at this angle somewhere here, okay, in this region is the electric field is there. Okay, so electric field is there in this direction. Then magnetic field is given as 4J plus 6K. Okay, so this is the magnetic field which is in the YZ plane. Okay, it is somewhere here. Now the question is, the charge particle is shifted from the origin. So charged particle shifted from origin. Charged particle shifted from the origin. It is moved from the origin. Charged particle is moved from the origin to a point, and that is given by the coordinate x is equal to 1, y is equal to 1. You have to find out the work done for this displacement of the charged particle. What is the total magnitude of work done? So the question is the total magnitude of work done. Sorry, this is magnitude. Total magnitude of the work done. Is, options are there in the denominator. We'll just directly solve and show you what is the value. Okay, so see, the question is saying that question is stated from it is taken from origin to some xy plane, because x is 1, and so it will be somewhere, if suppose this is 1 and this is 1, so it is actually shifted from here to here, this much. So this is actually, you know, from our so this can be, suppose this is P, this is O, so this OP vector you have to find out. So F into dr. Okay, so what is F and what is dr? So here, what is the force acting on the body? You have to first of all find out.
Hello,
Okay,
Ram.
so,
No screen. So Ram,
yes,
screen not shared.
screen is not share.
Yes, yes. I got network disconnected. Now I'm coming inside the net screen is not shared.
No, actually you are not visible in the meeting itself.
Oh, no, net
Somehow,
disconnected. Now I'm unable.
okay, I'll just reshare. Look, actually you are not in the meeting. I cannot see you in the meeting. Okay, let me reshare it. Now you have arrived. You check whether you can see now. I hope you will be able to see now. Hello, madam, are you able to see now? Okay, so we'll just wind up with this solution. Okay, look what was given. The charge was shifted. The electric field is given as 2I plus 3J. Electric field is given like this. And magnetic field is given as 4J plus 6K. Now the question is actually the charge particle is shifted from the origin to the point xy. See, from origin here to x is equal to 1 and y is equal to 1. So to this point, that means, you know, this magnetic field, you have to see this is in the y and z plane. Okay, this magnetic field is in the direction of, okay, so we can find out the direction from here. See, if this is y and this is z, actually this will be somewhat in this direction itself. Okay, so when we say v cross b, the magnetic force, so the